On January 12, 1965, America's brightest nuclear scientists gathered in the Nevada desert to witness something unprecedented: the deliberate destruction of a perfectly functioning nuclear reactor. This wasn't an accident. It wasn't a failure. It was the plan. The KIWI-TNT reactor sat on its test stand, designed from the ground up to explode. A controlled catastrophe meant to answer one terrifying question: what happens when humanity's most powerful rocket engine fails in the worst possible way? What they discovered that day would haunt the space program for decades and ultimately determine whether humanity would ever ride atomic fire to the stars. To understand why anyone would deliberately destroy a working nuclear reactor, you have to go back to a dream that consumed an entire generation of physicists and engineers. In the aftermath of World War II, as the space age dawned, America's rocket scientists faced a fundamental problem. Chemical rockets were never going to take us to Mars. They were too slow, too heavy, too limited by the basic chemistry of burning fuel. But there was another way, a revolutionary technology that promised to change everything. Project Rover began in 1955 with a deceptively simple idea. Instead of burning chemical fuel, why not use a nuclear reactor to superheat hydrogen propellant to temperatures that would make conventional engines melt into slag? The physics were elegant, almost seductive in their efficiency. A nuclear thermal rocket could achieve specific impulses of 800 to 900 seconds, roughly double the performance of the best chemical rockets, which topped out around 400 seconds. That difference wasn't just incremental, it was transformational. It was the difference between being trapped in Earth orbit and reaching the outer planets. It was the difference between Mars being a distant dream and Mars being a destination. Dr. Ted Merkel, one of the project's leading engineers, became obsessed with what he called the technical sweetness of nuclear propulsion, the raw power, the elegant physics, the sheer efficiency that made chemical rockets look primitive by comparison. The KIWI reactors, named after the flightless bird in a bit of dark humor about a technology that might never fly, represented years of incremental success. Each test brought new breakthroughs. Each problem solved revealed new possibilities. By 1964, the KIWI-B4A reactor had been successfully tested, proving that the fundamental concept worked. The graphite-moderated, hydrogen-cooled engine could superheat propellant to temperatures that would vaporize steel. The technical challenges that would have stopped lesser engineers: thermal stress, material erosion, the brutal environment inside a reactor core, pumping liquid hydrogen at cryogenic temperatures, had been solved, one by one. The dream of atomic spaceflight wasn't just possible anymore. It was real, sitting on a test stand in the Nevada desert, ready to carry humanity to the stars. But there was one question that kept nuclear propulsion grounded, one scenario that haunted mission planners in their sleep. What happens during a launch abort? What if something goes catastrophically wrong during ascent? What if the reactor goes critical uncontrollably, not in the controlled environment of a test stand, but tumbling through the atmosphere over populated areas? No one actually knew the scale of the catastrophe that would follow. Computer models could only tell you so much. Real-world physics always has surprises, and with nuclear reactors, surprises can kill thousands. To answer that question, to truly understand the monster they had created, Merkel and his colleagues would have to do something unprecedented. They would have to deliberately trigger the very nightmare scenario they hoped would never happen. Engineering a disaster is harder than you might think. The KIWI reactors had been designed with multiple layers of safety systems, each one carefully crafted to prevent exactly the kind of catastrophic failure they now needed to create. Transforming the KIWI-B4A into KIWI-TNT required inverse engineering, deliberately weakening systems that had taken years to perfect, removing the safety nets that stood between controlled operation and explosive disassembly. The modifications were precise and calculated. They altered the moderator cylinders and increased the reactivity insertion rate, ensuring the reactor would achieve what nuclear engineers call prompt criticality, the rapid exponential increase in reactor power that occurs when the nuclear chain reaction runs away faster than any safety system can respond. The team calculated the exact sequence. Withdraw the control rods rapidly, flood the core with liquid hydrogen propellant, and let physics do the rest. The expected energy release, equivalent to approximately 1 ton of TNT. Not a nuclear weapon, but a thermal explosion violent enough to tear the reactor apart and scatter its radioactive contents across the desert. There's a story about Dr. Ted Merkel that captures the all-consuming nature of this work, the way it invaded every corner of life. As his wife went into labor, Merkel sat in the hospital waiting room, drawing blast radius circles on maps of potential launch sites, calculating fallout patterns while awaiting his child's birth. It's a moment that crystallizes the tension between personal life and scientific duty, between the intimate human scale of a father waiting for his child and the vast, impersonal calculations of radioactive dispersal and acceptable risk. But there was another variable they couldn't fully control, one that would determine whether this experiment remained a scientific milestone or became a public relations disaster: the radioactive fallout. The KIWI reactor core contained about 40 kilograms of highly enriched uranium and several kilograms of fission products from previous test runs. During prompt criticality, as the core temperature spiked to over 4,000 Kelvin, hot enough to vaporize a significant portion of the graphite and metal, all of that radioactive material would be released into the atmosphere uranium particles. Fission products, a complex cocktail of radioactive isotopes including iodine-131, cesium-137, and strontium-90, each with its own half-life, its own biological pathway, its own capacity for harm. Radioactive dispersal is notoriously unpredictable. Wind speed, atmospheric stability, particle size distribution, all variables that could expand or contract the danger zone. The Nevada test site was chosen specifically for its remoteness and prevailing wind patterns that typically carried fallout away from populated areas. But typically isn't always. Weather forecasts in 1965 were far less sophisticated than today, introducing significant uncertainty into every calculation. The environmental scientists and health physicists who had to model the radioactive dispersal found themselves caught between their duty to enable the test and their responsibility to protect public health. Their calculations revealed uncomfortable truths about acceptable risk. The expected radius of radioactive fallout and contamination was up to 50 miles downwind for direct environmental sampling, with detectable fallout potentially reaching as far as 200 miles. These weren't just technical questions, they were moral ones. How much radioactive contamination of downwind areas was acceptable? How many people could be exposed to how much radiation before the test became unconscionable? The answers were classified at the highest levels. The test itself was wrapped in secrecy, with public information carefully controlled to avoid panic about nuclear explosions in Nevada. The political clearances were secured. The environmental models were complete, however uncertain. There was nothing left to do but execute the test. January 12, 1965, dawned cold and clear over the Nevada test site. Final weather checks confirmed acceptable conditions, not ideal, but acceptable. There's always a compromise between perfect conditions and schedule pressure, between waiting for the optimal moment and the institutional momentum that demands results. Personnel evacuated to bunkers and observation points miles away, leaving only remote cameras and instrumentation near the test stand to witness what came next. Dr. Harold Agnew, the senior physicist who had championed this test, watched from the control bunker with what he would later describe as a mixture of excitement and apprehension. This was the moment when theoretical physics becomes visceral reality, when equations transform into shock waves, when the elegant mathematics of neutron cross-sections and thermal expansion coefficients become fire and fury in the real world. The countdown sequence began. Liquid hydrogen began flowing into the reactor, a river of cryogenic fuel at -253 degrees Celsius, so cold it would freeze air solid, cooling systems activated. Then the critical moment. The control rods withdrew rapidly, far faster than any normal startup sequence would allow. The nuclear chain reaction began, neutrons splitting uranium atoms, releasing more neutrons, splitting more atoms, the reaction rate doubling and doubling again in a runaway cascade. Within 1.5 seconds, the reactor achieved prompt criticality. The core temperature spiked to over 4,000 Kelvin, hot enough to vaporize the graphite moderator, hot enough to dissociate hydrogen molecules into individual atoms. The thermal expansion was instantaneous and violent. Hydrogen pressure built faster than the reactor vessel could contain. The explosive disassembly tore the reactor apart with a force equivalent to approximately 1 ton of TNT. A fireball erupted from the test stand, a sphere of incandescent gas expanding at supersonic speed. Debris, chunks of graphite, twisted metal, vaporized uranium, scattered in all directions. A mushroom cloud rose into the Nevada sky, smaller than a nuclear weapon's signature, but unmistakably similar in form. The cameras captured it all, frame by frame, the destruction unfolding in slow-motion clarity. The explosion was more violent than some predictions suggested. Debris scattered across a wider radius than certain models had indicated. Instrumentation designed to survive the initial blast was destroyed faster than expected. In those first seconds, it became clear that even with all their calculations, all their modeling, all their careful engineering, nature had delivered surprises. But the explosion itself was only the beginning. The real test, the real danger, was what came next. The fallout. Radiation monitors detected the plume immediately, tracking its movement across the desert. The vaporized uranium and fission products created a complex mix of radioactive isotopes, each one carried by the wind in patterns that defied simple prediction. Particulate matter settled in unpredictable ways. Some areas showed hotspots far from the test site due to local weather anomalies, microscale variations in wind and terrain that no model could have captured. The actual path and deposition of the radioactive fallout plume differed from predicted models, traveling farther and depositing measurable contamination in areas not originally expected, including southern Nevada and California. Measurable levels of radioactive isotopes appeared in milk and air samples up to 200 miles downwind. Public health agencies tracked the dispersal, documenting contamination levels that, if publicly known at the time, would have sparked significant controversy. Cleanup crews faced contaminated debris scattered across the test site, twisted metal, chunks of graphite, fragments of the reactor vessel, all of it radioactive. Some pieces would remain dangerous for years, slowly decaying as their constituent isotopes transformed into more stable forms. The half-life of cesium-137 is 30 years. Strontium-90, which mimics calcium and accumulates in bones, has a half-life of 29 years. The KIWI-TNT test site would be a radioactive scar on the Nevada desert for decades. Despite the violence of the explosion, despite the surprises in the fallout patterns, the test was deemed a technical success. They had successfully modeled a worst-case reactor failure. They had gathered data on radioactive dispersal under real-world conditions. They had answered the question they set out to answer. But the answer was one that NASA and the Atomic Energy Commission didn't want to hear. The data revealed an uncomfortable truth. Even a controlled nuclear disaster in a remote desert produced radioactive contamination that couldn't be fully contained or predicted. The environmental and health risks highlighted by the test contributed to growing opposition and skepticism regarding the safety and practicality of nuclear rocket programs. If this had happened during an actual launch abort, over Cape Canaveral, over the Atlantic, over any populated area, the consequences would have been catastrophic on a scale that made the entire enterprise politically untenable. The KIWI-TNT test had answered the question it was designed to answer. But sometimes, proving you can control a disaster is the same as proving you shouldn't risk it at all. The death of the dream was slow, a gradual erosion rather than a sudden collapse. Additional reactor tests continued after KIWI-TNT. The NERVA program, nuclear engine for rocket vehicle application, followed Project Rover, developing even more advanced designs, pushing the technology closer to flight-ready status. The engineers achieved remarkable technical successes, solving problem after problem, proving again and again that nuclear thermal propulsion could work. But the fundamental problem remained unsolved. How do you make a nuclear rocket safe enough for public acceptance? The political climate was shifting. The 1963 Partial Test Ban Treaty had already banned atmospheric nuclear tests, and public sentiment was turning against nuclear activities that posed environmental risks. The specter of nuclear proliferation loomed over every discussion. Nuclear thermal rockets used highly enriched uranium, the same material used in nuclear weapons, and any launch failure could scatter weapons-grade material across a wide area. Environmental groups and public health advocates, learning of tests like KIWI-TNT through leaks and declassifications, began raising fundamental questions about the wisdom of launching nuclear reactors through the atmosphere at all. Dr. Ted Merkel and the project team faced the reality that their life's work, the reactor designs they'd perfected, the technical problems they'd solved, the elegant physics they'd mastered, might never fly the psychological toll of seeing a revolutionary technology shelved not because it didn't work, but because it worked too well, too dangerously, was profound. These were engineers who had dedicated years to solving impossible problems, only to discover that the real impossible problem was political and social, not technical. In 1973, Project Rover was canceled. The official reason cited was budgetary constraints and changing national priorities, particularly the end of the Apollo program and reduced interest in crewed Mars missions. But everyone involved knew the deeper truth. The environmental and political costs were deemed too high. The total program cost had exceeded $1.4 billion in 1972, a staggering investment that produced working nuclear rocket engines that would never fly. The tragic irony of KIWI-TNT is that it proved both too much and too little. It proved that the worst-case scenario was survivable and measurable, that scientists could understand and model a catastrophic reactor failure. But in doing so, it made the worst-case scenario real and tangible for policymakers and the public. It transformed an abstract risk into concrete data about radioactive contamination spreading hundreds of miles, about unpredictable fallout patterns, about the impossibility of guaranteeing safety when dealing with nuclear reactions in the atmosphere. The legacy of KIWI-TNT extends far beyond the Nevada test site, far beyond the canceled programs and the billions of dollars spent. It represents a fundamental question that still haunts space exploration today. How much risk is acceptable in the pursuit of the stars? How do we balance the revolutionary potential of dangerous technologies against the responsibility to protect the environment and public health? The nuclear rocket engines developed under Project Rover and NERVA were engineering marvels, machines that could have cut travel time to Mars in half, that could have opened the outer solar system to human exploration. They worked, they were real, and they will probably never fly, not because we can't build them, but because we chose not to accept the risks they represent. That choice, made in the shadow of KIWI-TNT's mushroom cloud, informed by data about radioactive dispersal and environmental contamination, reflects a maturation of the space program, a recognition that technical capability alone doesn't justify deployment. Sometimes the most important scientific result isn't a number or a measurement, but a decision about what not to do. The KIWI-TNT test site remains in the Nevada desert, a radioactive monument to ambition and restraint, to the dream of atomic spaceflight and the reality of environmental responsibility. The reactor fragments have long since been cleaned up or buried, but the isotopes remain, slowly decaying, slowly releasing their energy into the desert sand. In a few more decades, the cesium-137 will have decayed to half its original activity. In a century, it will be mostly gone. But the question KIWI-TNT raised will remain, what are we willing to risk to reach the stars? What price in environmental damage, in public safety, in the possibility of catastrophic failure, is acceptable for revolutionary capability? These aren't questions that science alone can answer. They require us to confront our values, our priorities, our vision of what humanity should become as we reach beyond our planet. On January 12, 1965, America's brightest nuclear scientists deliberately destroyed a perfectly functioning nuclear reactor to answer one question. They succeeded. The answer they found changed the course of space exploration, not through failure, but through a success that revealed costs we were unwilling to pay. The mushroom cloud that rose over Nevada that day cast a shadow that still falls across our dreams of Mars, of the outer planets, of the deep space missions that nuclear propulsion could enable. Perhaps one day, with better technology, with safer designs, with a different calculus of risk and reward, nuclear rockets will finally fly. But they will fly, if they fly at all, because we learned the lessons of KIWI-TNT, that power without wisdom is dangerous, that technical capability without social acceptance is unusable, and that sometimes the bravest thing scientists can do is acknowledge the limits of what should be built, not just what can be built. The dream of atomic spaceflight didn't die in the Nevada desert on January 12, 1965. It was transformed, tempered by the reality of radioactive fallout spreading 200 miles downwind. By the recognition that some technologies demand more careful consideration than others, KIWI-TNT was designed to fail catastrophically, and it succeeded perfectly. In doing so, it taught us that not every success is worth celebrating, and not every capability is worth deploying. That lesson, purchased at the cost of $1.4 billion and a radioactive scar on the Nevada desert, may be the most valuable result of the entire nuclear rocket program. If you enjoyed this story, hit subscribe for more stories where history, technology, and human ambition collide. Thanks for watching.